what is an electric field? So to answer this question, it helps to think about gravity first. So what we're going to do is we're going to recall. Okay, so gravity. I'm going to use a very similar analogy to what we used to talk about the forces of attraction. So we have, for instance, the Earth. And we know the Earth has a gravitational field all the way around it, and it pulls objects towards it. So we have that the Earth would have some mass, and we would have that there'd be another mass somewhere out here, or on the surface of the planet, somewhere in the vicinity of it. And what we would see is that, again, somewhere along this line connecting their centers, we would see that force of attraction. So for instance, on this mass here, away from the Earth, we would have that there's a force pulling towards the Earth, force of gravity, Fg. So we like to define some quantity that doesn't depend on having this mass here. So in other words, we would like to be able to say that Earth has a gravitational field all around it, regardless of what else is happening around it. So whether if this mass is here or not, there should still be gravity around it. So what we do is we define some gravitational field. We say that, for instance, in gravity, the gravitational field is just the force of gravity divided by the mass. So we divide the mass out, this being this little mass m here, and we would find that there's an expression that does not depend on this mass being present here. So I should be able to say that whether if this object is here or not, Earth's gravity is still present. The way it works is that the gravitational field will be defined in the direction that the force would act on what's called a test mass. In other words, if you were to put a mass there, the direction that it feels a force in is the direction of the gravitational field. That's what it's defined as. So what we'll do is we'll use that analogy for electricity, so versus electricity. For the sake of this analogy, I will use a negative charge, analogous to the Earth. So here's a negative charge of some sort. And what I would do is I would put some sort of test charge in the presence of it. This positive charge, let's say. So we have a positive test charge. We know that if we have this line that connects the two charges, then the force on this positive charge should point directly along this line towards that other charge. Call this force Fe, the electric force. So by the same ideas here, we would say that whatever direction that this electric force acts on a positive test charge is the definition of the direction of the electric field. In other words, at this location, we would say the electric field would point along that direction of that force along that line. So we call that E for the electric field. If I were to put this charge anywhere else around this negative charge, we would find that the force would point towards it everywhere, no matter what. So regardless of whether or not this charge is here, so if we just remove this charge completely from the picture, we can still talk about some electric field that points towards this negative charge, which we're going to call E. So E, being analogous to the gravitational field, would be the electric force instead of the gravitational force. So force electric divided by not the mass, but the charge. Let's call this lowercase q, and let's call the other charge capital Q. So we divide out the test charge from the equation. A lot of times this is written in a single line, So in other words, the force electric is just the product of the charge put in some electric field. So a lot of times this is what we go to right here. Okay. But this is where we get the idea of what an electric field is. Okay. So now if we use the same idea for the other kind of charge, because here we did it for a negative charge, if we instead did this for a positive charge, we would find that if we put a test charge in the presence of that, we would know that that force would not be attractive, but it would be rather repulsive. So it would point away from it along that line. So using the same definition, the electric field is defined to point in the direction that a force would act on a positive charge if it were put there. So the electric field points also away from that positive charge. And no matter where I put this test charge around here, I would say that the force points away. So therefore I would say that the electric field points away from that positive charge no matter where I am. That's our electric field E. And again, this charge is only here to help us understand where the direction of the electric field comes from. But again, we don't need to have that this charge be here. This is one single lone charge by itself, and it emits electric field everywhere around it. So we find that for negative charges, the electric field points toward it. And for positive charges, the electric field points away from it in every single direction. So this is how it works for point charges. Every time you have a point charge, the electric field will either point all away or all towards it. So according to this equation here that we have for the electric field, if it's just the force divided by some test charge, what we would have is that the force is given by Coulomb's law. Force given by Coulomb's law. And this force is the force between two point charges. So we would have that electric force would be K, capital Q, lowercase q, over r squared. So we have the two charges of interest, one being the test charge, and the other one sometimes being referred to as the source charge, the source of the electric field, and then the distance that separates them. So we have this. So if we were to plug this into here and divide out the test charge, we would have that the expression for the electric field of a point charge is just simply K, capital Q, over r squared. So where Q is defined as the source charge, okay? It is the source of the electric field that will then act on every other charge.